Subtree of another tree. This is another easy problem for the trees category, and let's look at the problem statement. The problem is, given the roots of two binary trees, root and subroot, return true if there is a subtree of root with the same structure and node values of subroot, and false otherwise. So what it basically says is that we have a root and a subroot. Now it says over here, given the roots of two binary trees, we have root and subroot. So this is subroot and this is root. Return true if there is a subtree of root. So if there is actually a subtree of root, okay, with the same structure and node values of subroot, the same exact thing like what subroot has, 4, 1, 2. If it has 4, 1, 2, then we could return true. If not, we could return false otherwise. A subtree of a binary tree is a tree that consists of a node in tree and all of the node's descendants. The tree could also be considered as a subtree of itself. Now, it's a little, let me just break it down. A subtree of a binary tree. So a subtree of a binary tree, which is called tree, right, is a tree that consists of a node in tree. So there's a node that consists in a tree and all of the node's descendants. The tree could also be considered as a subtree of itself. Now let's go and look at this example. I hope you got this last point across. I'm just going to repeat it for the last time. A subtree of a binary tree, which is tree, right, is a tree that consists of a node in tree and all of the node's descendants. The tree could also be considered as a subtree of itself. So basically this thing of itself could also be called subtree. I hope you got this point. And these subnodes could also consist of whatever the this is a subtree and this is part of the tree, and this tree is also called a subtree of itself, right? That's the entire explanation. Here we have the input, which is root. Now root has 3, 4, 5, 1, 2. If we look at this root, we have 3, 4, 5, 1, 2, and the subroot has in the list 4, 1, and 2. Now we look at this. This is true because 4, 1, 2 actually exist here. So 4, 1, 2 exist here. That's why we return true. Now example 2 has root, and we have 3, 4, 5, 1, null, null, 0, and then if you could look at it, so we have 3, 4, 5, null, null, null. How is it like null, null, null? 3, 4, 5, null, null, and then we have null, null, and then we have one more null. Basically, I think I'm null, null, and then we have 1. And then we have 4, 1, 2 over here, and then we have false. I don't know. Let me just confirm this. We have 3, then we have 4, 5, and then we have then we start from 1 and then 2. Okay, then I was doing it wrong. So null and then null and then null and then so we have null and then null, and then we move on to over here, which is null, and then we have 0, and essentially that's the thing, right? I totally get it now. And then we have, for subroot, we have 4, 1, 2, which is this, and then we're checking if it exists here, and it does. I mean, it doesn't actually. The reason why this is not right is because this is actually 4, 1, 2 false. Now over here we have a little bit of different structure, and that's why it's not giving it as true. The constraints here, the number of nodes in the root tree is in the range from 1 to 2000. The number of nodes in the subroot tree is in the range from 1 to 1000. And then we have the node root value, which is between minus 10 raised to the power 4 to 10 raised to the power 4. And then we have the subroot value, which is in between minus 10 raised to the power 4 to 10 raised to the power 4. So minus 10 raised to the power 4 to 10 raised to the power 4. So basically this is the entire criteria here. So these are the number of nodes, and let me just actually take a picture of this. Want to go a little step further. I'm going to take a screenshot of this. So let me just grab this part. 1 second. So not that, but actually a little more till here. And we're gonna go to paint, which is P-A-I-N-T. And we're just gonna open up the application. And over here, what I'm gonna do is I'm gonna Control V. Got this. To maximize, and then just show you that we have the starting from here. So let me just get a marker. I'm just gonna get this. So I mean, I could get a brush. Yeah. So over here we have this root. So we start from here, okay? Then we basically go here. So 1, 4, 5, okay? And then we have from here. So 1 and then 2. And then we have null, which is this, and then null. And then normally you see that we have over here this part. So essentially this all is null, and then this is 0. So we could just say simply, you know, the thing that was corresponding here, that we have null, and then a completely null, and then 0 over here. While the subroot is 4, and then 1 and 2. And then we say false here. Okay, so now let's think up the solution. Again, remember, this is a tree problem. You think about trees, you have what? You have a Boolean return type is subtree. We have a tree node pointer, which is root, and we have tree node pointer subroot. And we're starting with the root and the subroot. What might we do? Well, there's always going to be some kind of scenario here, a scenario that we might have to, you know, come across. Now, the thing is, we have is subtree, but we might need to find a function. Remember the last problem we did was is same tree, and we use this function to get the same tree, right? Functionality. We could use the same exact stuff, but use this function to find the subtree of another tree. So what I'm talking about here is that first of all, we create a function to find the same tree, okay? I'm comparing two trees and I want to see if they're same, okay? So that's exactly what I want to do. I would go here into the public section, and then on top of here, so right here, I would have a Boolean. So let me just maximize the screen a bit. So what I want to do is I want to have is same tree, okay? Now is same tree has two things. We have a tree node pointer left, and then or a P, and then we have a tree node pointer Q. So tree node pointer, and we have Q. Now what I'm gonna do is I'm gonna have to check if P and Q are same. So if I say if well, if P and Q are not null pointer, so if I say P is equal to null pointer, and then we have equal to, or maybe and we have Q is equal to null pointer, okay? If I do this, I could simply say return false, or maybe true because they're same, right? Because they are same. And then there was another condition where we said if P is equal to, basically it means like if one was, if P is equal to or null pointer, or Q is equal to null pointer, right? This was the condition where 1 is a null pointer. So if that was the condition, I would say false because, you know, they're not same. Right now we're just simply having that same, you know, question, that, you know, finding the same tree problem. Previous video, you will check it out. So we're basically implementing the same solution here. Now, okay, so now we had that recursive case here where we basically go into our, you know, sub levels. But first of all, we check the value. We check the value of our current pointer. So we say P value. If it equals to the Q's value, we essentially have to go underneath. So what we're gonna go is under the hood, and we're just gonna keep going. So we have P and Q, and we're gonna have to check in, you know, what we have to do. If we have to basically recall is same tree over and over, because we first of all checked this case, which is P's value and Q's value. Now let's look at the same tree problem just to show that you understand everything over here. Now I wish the diagram was there. I think it's this one. So you know, same values, right? 1 and 1. Then we go to the next subtree, which is left, left, okay? And then we go right, right. We're basically checking, first of all, the root values, and then we're checking the left values, and then we're checking the right values. And make sure that everything is true, right? That's exactly what we want to do. So we want to have, first of all, this one, which is the root values. Then we want to have, wait a minute, so root values, and then we want to check the left values. So we have is same tree, and then we have p left, and then we have q, which is right here, q right, okay? And then we have ampersands again, and we have is same tree, and then we have p right, and then we have q right. Okay, so essentially we're gonna keep going until we bump up to the end and we have everything matching. If it's matching, it's gonna return true. If it's not matching, it's gonna return false. And this is our base case. That's our successful is same tree problem. Now let's go a little step further, and now we have this is same tree. We could use this with our is subtree problem because we have to check in a root level if if they're same or not. So what I could do is we have the root pointer and then we have the subroot pointer. Simply right now, again, this is a tree problem. Use the base cases and then use recursion to solve it out. That's basically the way to approach these problems, tree problems especially. So we have if the root is if root. Now one way I want to say is that you could basically have simply like this, root is equal to null pointer. Other way you could do is you could say exclamation root. If this means if the root is null pointer, you could just return false. Okay. So what I would prefer is just keeping it like root is equal to null pointer, just so that it's a little concise. I mean, it's like more common, just to keep it same and organized. Now what we want to do is we want to have the next part, which is if the now you got my point here. We had the root. If that was null, basically the question was false, because we're trying to look for a subroot within the root, and if that root is just empty, then what's the point of this problem? And it definitely should be false. Now we have to check the same tree thing. So what I'm gonna do here is I'm using this is same tree function, which I created here, right? What does it accept? It accepts a p and a q pointer. So the p and q would be simply my root and subroot. So let's invoke this function by calling it as is same tree, okay? And I'm gonna have the p and the q inside, and I'm gonna check whether actually not p and q. In this case, it would be root, and then it would be subroot. Now subroot would be like this. Now both of them will be in here. Now, for instance, if everything goes out well here, because this actually returns Boolean. So if this is true, then we return. Essentially, it would return true, and if it is true, we will return true. And if it breaks, we could return false. So we found the same tree. Now we have to return it. Basically, this is a recursive call. We have to check the root and subroot, but we have to essentially check for each level, right? This is the trick here. We have to check for each level. So you have to go and do a recursive thing over here. We have to do is subtree. We have to call is subtree. So is subtree. And then what it accepts is it accepts root and subroot, right? So we're gonna say roots left. Okay, we'll compare with subroot. Okay, if that is there, or if is subtree, because it can either be on the left or it could be either on the right side, right? We don't know. So we say root right, and we have comma subroot. Okay, so this is the case here. We have either the left or the right. If it comes like that, we just simply return it. And you already know what this is subtree is returning. It's returning either true or false, right? So it's either going to return true if it's same, false otherwise, and entirely this is our solution. So these are two functions. This is being used within this one, and that's pretty much the solution. Let's try and run it first of all. So we have control and comma. When I do this, I have a test result and a compilation error. So what is it? It says in line number 24 we have character 20 error, no member named value. I made that mistake last time too. So we have to go to line number 24, which is right here. And over here we have the value, and you can see over here the struct is defined like this with int val. So we have to make sure that we follow its same syntax style. Okay, so now let's control and comma this and see what happens. So now we have wrong answer. So over here in case 1 we have brute is 34512, this one, and then 412, and then we said output ours came as false and expected was true, while the other case worked actually. So what could be the issue here? Well, we have this null pointer and true, and then we have this, it could be false, and then we have this, which is looks good because we're basically doing the same here. And then we have this thing, which is root is equal to null pointer, return false. And then if same tree, we have return true, and then we basically go here and check for each portion. What I'm thinking is maybe instead of the null pointers that I was thinking, maybe just have not root, just to see if this actually works. So not root here, and then try it out maybe. So just one try with this. Okay, the same issue, but what we're going to do is we're going to make sure that these null pointers, remember it's the same thing. Null pointer is equal to not p and not q. This means the same exact stuff. Same thing goes for here. We have just a shorter way to write it. So not p, and then we have not q, and then we basically put it within this, and I could run it control and comma. Okay, so we still have the issue. Interesting. I'm going to look at the solution over again. So we have bool is same tree, p and q. If this is there, we return true. And if something is like that, we return false. Then we have this p value and equal to q value. And if it's same tree is left and right, and if same tree is right and p, q, p, q, looks all good. Return this value. Boolean is subtree. We have root and subroot, and over here we have if root not root, then we have return false, and we over here is same tree, and we have root and subroot. Now the thing is, we have if this is same, we return true, and the return is subtree, root left, root, subroot, or we have is subtree, root right, and then we have subroot. So essentially we have this as the goal. It should work now. I'm trying my best to make it work. It looks correct, but I don't know what's the issue. Okay, so when you basically get stuck here, you could use a little bit of ChatGPT just so we could fix out what's the issue. So you could basically copy this. So just copy this. Okay. Yeah. So I'm gonna say over here. I'm gonna say this is the problem. So I'm gonna say, right. So we just copy this. The following is my C++ solution. So you just type in your C++ solution, which is this is our C++ solution. So we just copy this and paste it here. What is wrong in this? Okay, so it's going to tell us the issue is in the same tree functions, specifically in the recursive call to check the subtrees. So same tree function. Wow. You have return p value and q value is same tree. We have p left and q left, q right, and then we have the same tree. It looks the same, but okay, it had right. Why do we have right? Wait a minute, did I just mistakenly? Wow, I mistakenly typed this. It was left and then right. Okay. So you know sometimes you just make minor mistakes. So this was a really rookie mistake. Control and comma, and this should give you the solution now. What? Now we have another issue here. So we have left and right and left and right. So here the second recursive call should be comparing p right with p left. Instead, q right. This is because, okay, then the correct line should be return p value, q value is same tree, p left, p q right, q left. Oh, okay. So I mean, I'm doing something wrong here. I didn't do it properly, because the reason what I said is that if the both values are same, then you go and compare p's left with q's right, with actually q's right. Well, actually, you have to do compare with left. So p's left with q's left, okay? And then you compare p's right with q's right. So like this. And this is what I'm believing. And this should be the answer. Control and comma. Wow, we had that, small, pretty, junior rookie mistake, but we kind of got the solution accepted and approved. Okay, so the last thing what we're going to do is we're just going to check the explanation here, just so that it aligns well. So I'm going to say explain the following C++ code, and I'm just going to paste it in right here. Okay, so now if we check this, let's break it down to step by step. Tree node structure. First, let's understand the tree node. Okay, structure. It's a basic structure representing a node in a binary tree. Each node has an integer value val and 2 pointers to other nodes. Then one for the left child, left, and one for the right child, right, is same tree function. The function compares two binary trees to check if they are exactly the same. It takes two tree node pointers, p and q, representing the roots of two trees. The function returns true if both trees are the same and false otherwise. Now, the first if condition checks if both p and q are a null pointer, meaning they are both empty trees. If so, it returns true. Remember the null pointer part where we had it over here. So if this is null pointer and q is null pointer, return true. So meaning both are empty trees. If so, returns true because two empty trees are considered the same. If the second if condition checks if either p or q is null pointer while the other is not. And now in this case, the trees can't be the same, so it returns false. If neither of the above conditions is met, it compares the values of the current node. So we have p's value and q's value. If they are not equal, the trees can't be the same, so it returns. So basically, it compares the current node. So we have, it compares the values of the current node. So we have values p and q's value. If they are not equal, the trees can't be the same, so it returns false. Just like what it's saying over here, we compare each value. Now current one. Okay, if this is true, then we go into this part where we recursively call and check the left side with the q's left. So I'm talking about here. So we have this. Just imagine this is in this one we're comparing. So we have p left and q left. We're comparing 1 and 1. Okay, and the same thing we're doing is for p right, which is 2, and q's right, which is 2. And we see if the values are same. So if the values are equal, they recursively. So If neither of the above conditions is met, it compares the values of the current nodes, p, value, and q. If they are not equal, the trees cannot be the same, so it returns false. If the values are equal, it recursively calls isSameTree for the left subtree and the right subtree to compare them as well. At the end, the result is true only if the current nodes have equal values and both the left and right subtrees are the same. Okay? Okay, so isSubtree function is the function that the function checks if a given tree subroot is a subtree of another tree. So yeah, it takes two tree node pointers, root and subroot, representing the roots of the main tree and the potential subtree respectively. And then if the root is null pointer, it means there's no tree to search for a subtree, so it returns false, really easy. And then if the subroot tree is the same as the root tree using isSameTree function, then subroot is indeed a subroot tree of the root, so it returns true. Another step here where we basically have, if it's the same, we just do this. Essentially, and then the last case where we have this one, where recursively, if subroot is not a subtree of the root, it recursively checks if subroot is a subtree of the left subtree of a root. If subroot is not a subtree of the root, it recursively checks if subroot is a subtree of the left subtree of the root or the right subtree of the root. I mean, you understood that we're basically recursively checking and if it's the left subtree or the right subtree. We don't know, so that's why we have this OR condition. And if it's true, otherwise we'll basically have return true. The function returns true if subroot is found to be a subtree in either the left or right subtree of root, otherwise it returns false. So in summary, this code defines two functions to compare binary trees and checks if one tree is a subtree of another. It does so by recursively comparing nodes and their subtrees. I hope you understood this problem pretty perfectly. Now, stay tuned for the next one.